Hey guys, I'd like to welcome you back. We've been talking about counting, and what we want to do now is apply counting to probability. So let's get started and let's talk about what we even mean by probability. Let's say that you were tossing a coin. If I handed you a coin and asked you, okay, what's the probability that when you toss this coin, you get heads? Most people would say something probably 50%. Other people might say 0.5, one half, and those would all be correct, right? There's a 1 in 2 chance that when I toss a coin, I get heads. Now, what if we tossed it one time? What would your experience tell you? Well, if I tossed it only one time and got heads, my experience tells me I get heads all the time. That sounds crazy because we really think that it's different. But if I tossed it, say, 3 times and got heads all 3 times, your experience would tell you that you get heads all the time. So what I've done is I've created a simulation, and I want to show you what this simulation is. What I've done is I've taken and decided to make heads the value 1 and tails the value 0. And then I've told Excel to go ahead and flip or toss the coin, in this case, 5 times, and then figure the probability. I got 2 heads out of 5. 2 over 5 is 0.4. Over here, this column was 100 times. And when I tossed 100 times, I wound up with 47 heads. And then this column over here, I did it 1,000 times. And when I did it 1,000 times, my probability is 0.49. Now, none of these are 0.5, right? And really, I could redo this. I've done this so many times. There's been plenty of times when I've rolled 5 times and I've gotten 4 out of 5 heads. And again, that's your experience, right? Your experience tells you that you get heads 4 out of 5 times. It's hard to argue with experience. It is what it is. But yet, this number 1/2 is the first thing that came into your mind, right? When I said, what's the probability of tossing a coin and getting heads? None of you paused the recording and ran off and got a quarter and started tossing like mad, right? And said, okay, how many heads did I get? No, you said, it's heads or tails. One of those is heads, so 1/2. So what's going on here? Well, really, the tension is that there's 2 notions of probability. And the first one is, bring up my notes here again, is what's known as experimental or empirical probability, right? Empiricism, what can we observe? And so that probability of an event E occurring, this says, let's just figure out, let's count the number of times E occurred divided by the total number of times we played the game. So if I tossed a coin 15 times, that's my denominator. How many times I got heads, that's my numerator. As opposed to the theoretical, or also known as classical probability, where here it's more of a thought experiment. How many ways can the event occur? And then what are the total number of possible outcomes? This is how most of you thought about it. You said there are 2 possible outcomes, one of which is the thing I actually want to have happen, right? One of the 2 outcomes is heads, therefore 1/2, 0.5. But go to Vegas, or maybe not go to Vegas. Rarely is that a good idea. But you go to Vegas and you have people that are experiencing a quote winning streak, right? Their experience is telling them that they're winning, and it's getting them to keep going. What they've done is they have essentially done this. Watch, I'm going to show you here something interesting. let's come back to my list here. Remember that ones represent heads. So in this list of 1,000, you'll see some strings, right? Let's find, oh, so right here. Right, here's a string of 4 ones. So maybe someone came into the game at this point and they said they played once, they lost. Said, well, I'm gonna play again. And then they won. And then they won again. And then they won again. And again. They lost again, but look, they won 2 more times here. If you're just in this little chunk, 1, 2, 3, 4, 5, 6, out of 8, that's 75% of the time. This person is experiencing getting heads 75% of the time. Play this game somewhere. I mean, you could go down this list and look for strings. Oh, look at this person. Look at this. And this was done randomly. 1, 2, 3, 4, 5, 6, 7, 8. This person, if you do it 10 times, is getting heads 80% of the time. You're not going to argue with them. But again, the big picture is this. Oh, there's your 8 ones, but boy, there's some zeros. In fact, let's go look. Can I find a bunch of zeros? I bet I can. I bet I can. There's 3 in a row. Okay. Oh, there's some, right? There's all the, oh, here we go. 1, 2, 3, 4, 5 zeros in a row. Right? I can just as easily find strings of zeros. So the idea here is that really you've got what's known as the law of large numbers. And that's where these things reconcile. Yeah, I may win a game 8 out of 10 times, but if I play it 1,000 times, I'm going to win. My winning percentage is going to be more closely aligned with the actual probability. And that's the law of large numbers. As the number of trials increases, the more times you do something, the experimental probability approaches the actual or theoretical probability. And really, at the end of the day, probability is based on counting. So let's do this. Let's look at some examples and connect probability to counting. So a coin is flipped 4 times. Let's start by listing the sample space. So the way I'm going to do that is I'm going to start by saying, okay, well, I could get all heads. Any other ways to get all heads? No. And then I could get 3 heads. So let's go through all the possibilities for 3 heads. Okay. Tails, heads, heads, heads. Did I miss any? We got the tails in the last spot, 3rd spot, 2nd spot, 1st spot. All right, and we could get 2 heads. Heads, heads, tails, tails. Heads, tails, heads, tails. Tails, heads, tails, heads. Tails, heads, heads, tails. Tails, heads, tails, heads. Or let's see, tails, tails, heads, heads. I get them all? I believe so. We can get 1 head. Heads, tails, tails, tails. Okay. And then we could get no heads. Well, let's see. What do we have here? 1, 2, 3, 4, 5, 10, 11, 12, 13, 14, 15, 16. So and we should expect that, right? We're tossing 4 times, and there's 2 options each time, 2 to the 4th power, right? So the sample space has size 16, okay? In other words, that's the number of possible outcomes. That is our denominator, okay? So find the probability of getting 3 heads. Well, the probability of 3 heads equals, well, I know that there are 16 possible outcomes, right? There is not any other possible result than what is listed in this space, the sample space. So there are 16 possible outcomes. Now, 3 heads, exactly 3 heads, right? Because technically, if I hadn't said exactly 3 heads, doesn't 4 heads also include 3 heads? Yeah, so I want to say exactly 3 heads and no more. So how many are there? Oh, there's 4. So the probability is 4 over 16, or 0.25, okay? All right, how about the probability of getting 0 tails? Well, that's going to be the same as getting all 4 heads, right? So how many ways are there, or how many outcomes have 0 tails? Oh, just 1. So this probability would be 1/16, which if you want, you could convert that to a decimal. No problem doing that if you want. And 0.0625. Okay. How about the probability of getting at least 2 heads? Probability of at least 2 heads. Well, what does that mean? That really means the probability of getting 2 heads, or 3 heads, or 4 heads. So let's go count. Well, 2 heads. Right here. There are 1, 2, 3, 4, 5, 6 ways to get 2 heads. There are 4 ways to get 3 heads, and there is 1 way to get 4 heads. So 6 plus 4 plus 1, right? 2 heads is 6 options, then 4 options, then 1 option. And so that gives us a grand total of 11 of those 16, which again, if we want to write this as a decimal, 0.6875. 0.6875. All right. And how about this one? Exactly 3 heads, or exactly 2 tails. Well, the 3 heads, we counted the 3 heads. There were 4. And the 2 tails, that's the same as saying 2 heads. Those are 6, right? 4 ways to get 3 heads, and 6 ways to get 2 tails. So that's 6 ways, 4 ways. So there were 10 total, 10/16, okay? Which is also 5/8, which you might know that off the top of your head, 0.625, okay? All right. So what was nice about this example that we just did with the coins is that the coins, right, the coin example, we are able to use just, get our hands on the sample space and then just count literally with our fingers, right? 1, 2, 3, 4, and so on. What I want to do next is something a little more complicated. Let's next look at where maybe we can't just list everything out. We have to kind of trust some of those other counting procedures that we had. So that's where I want to go next. All right, so let's look at this next example here. 6 friends are in a class of 25 students. The professor decides to form groups of 4 students. So what is the probability that a group is made up entirely of those friends? In other words, you've got a group of 4, and all 4 of those came from that group of 6. Well, let's think about this. The total number of outcomes, right? I know that's my denominator. I got to count, right? I'm going to have the number of groups with 4 of those 6 friends in them divided by the total number of 4-person groups. Okay, so the total number of 4-person, I'm sorry, let me say it this way. Total number of possible 4-person groups. Well, we're counting. We have 25 students. We're building groups of 4. Do we care about the order? No, right? All we care is who makes up those 4. So this is really a combination. Okay? And so we have a formula for that. And then I'm going to come back to it though. Let's talk about our numerator. So the total number of 4 friend groups. In other words, from those 6, how many ways can 4 of those be in a group? Well, now we're picking just from the set of friends, right? Okay. And so we can go compute those. Let me pull up my fancy calculator here. And let's see what we get. So we have 25C4. I'm going to tell you what that number is here momentarily. One, 2, 6, 5, 0. Whoops. 1, 2, 6, 5, 0. So 12,650 groups. And then we're going to do 6 choose 4. 15. Okay. And so the probability that you have all 4 friends is going to be 15 over 12,650. Which, if I'm going to go, you know what, I'm going to go out 4 decimal places. So 0.0012 if I'm rounding. 0012. Okay. Let's try this again. Probability that a group has exactly 2 of those friends. Why don't you give this one a try? So again, my denominator is still going to be that group of 25C4, all combinations of 4 students out of 25. But my numerator is 2, there's really 2 things going on, right? I've got 2 friends coming from a group of 6, and remember it's a group of 4, right? So the other 2 people are going to come from the non-friends. So how many non-friends are there? There's 25 total, 6 are friends. That leaves 19. So what this says is that 2 are coming from the friend group and the other 2 are coming from the 19 non-friend group, okay? And then what do we get? Well, we can actually do this all at once here. So I'm going to take my 6 combination 2 times and 19 combination 2 divided by, so that's 2565 if you're checking your work along the way, divided by 12,650. So 2565 by 12,650. 0.2028 if I'm rounding. Okay. So this one was a little more complicated. And again, I would encourage you to spend some time digesting this numerator, right? Because it's not just enough that you had 2 people coming from the 6. You also have to consider where the other 2 people come from, right? These are the 2 that came from the friends. These are the 2 that came from the non-friends, joined by, right, multiplication. Because this is fundamental counting principle, right? How many ways can I pick 2 people from the friend group times the number of ways I can pick 2 people from the non-friend group? All right, next, let's talk about odds. So the odds of an event occurring is the following ratio, the number of ways that the event can occur over the number of ways it cannot occur. Okay, so it's related to probability, but it's really, you're looking at favorable to unfavorable. Okay, so the odds of rolling a 5 on a 6-sided dice. Well, there is 1 5, and there are 5 non-5s, right? You've got 1, 2, 3, 4, 5, 6. Here's the 1 5, and here are the numbers that are not 5. And so the odds are 1 to 5. Okay? There's a 1 in 5 chance, or a 1 to 5 chance, right? Notice that numerator plus denominator is the size of the sample space. Okay. How about the odds of tossing a fair coin and getting heads? Well, it's going to be heads or tails. The odds are 1 to 1, right? Or just 1. A basketball player makes 79% of his free throws. What are the odds of him making his next free throw? Well, if he makes 79%, then he misses 21%. And so the probability, I'm sorry, not the probability, the odds of making would be 79 to 21. Okay. All right. So that's a little introduction to probability, specifically how counting is involved. In your academic futures, you're going to most likely take an entire class on probability and statistics, where you'll experience a much deeper analysis, and you'll learn some specific rules and how to define things like independent events and mutually exclusive and all sorts of wonderful theory and apply it. For now, at this point, I just want you to be able to count and see how counting is related to computing probabilities. All right? So spend some time digesting this, work back through these examples, and I will see you guys soon. Until next time.